All right, so to start off today, I want to go over the Bruce Banner example again, but let's see this in the debugger. And I want to show specifically how the object types are moving around this code and how the Bruce Banner object is changing state. So just a quick reminder, we have a Bruce Banner class that has several methods. Let me resize this. That has a state variable of type state, which is going to be initialized to Dr. Banner. And then we have 4 methods where we don't have any functionality defined in the Bruce Banner class. We simply defer to the state variable for its functionality. So whenever, for example, make angry is called, Bruce Banner has no defined behavior for make angry. Bruce Banner is just going to ask its state, hey, state, whatever state I'm currently in, call your make angry method. In the initial state, we'll get the Dr. Banner method, but if the state changes, we'll get different behavior based on the type stored in this state variable. We have several different types. Dr. Banner, when he's in his human form and he can drive a car, he can do the things that we saw last time. The Hulk state, when he gets angry, he smashes cars. And Professor Hulk, where he's as the Hulk, but he's also controlling himself and can maintain his rage. So we have these 3 states, and the car class I don't show in the slides just because it's extra clutter on the slides. It doesn't have any functionality, but the drive method takes an overweight boolean, and I do have a conditional, so it looks a little gross when I'm banning conditionals. But it's just not important to the example. I could actually add, and I thought about doing this, is adding the state pattern to the car where the car can be in a totaled state or a functional state. We could certainly do that as well. I just didn't do it. So I used a Boolean flag and this conditional, which just seems so out of place in this learning objective. So let's run through our program. I have the debugger running, and let's see how this program executes, focusing on the state of the stack and the heap. And I won't, not until learning objective 4, I believe, I have one in LO3, but I won't do very many slides showing the stack and the heap again, ever since the RPG example. But I will go through the debugger and show you that same information. The debugger will have the same information that I do in the slides in those examples, and that's where you should be at in terms of stack and heap. Being able to see what's going on in the stack and heap, you should be able to run this debugger, especially for studying for your quiz and interview on Thursday. You should be able to run the debugger and be able to read what's happening on the stack and what's happening in the heap through the debugger. So I want to give an example of that. So hopefully by the end of this example, you'll be able to generate your own stack and heap examples with any code that you want and be able to see what's happening in the stack and heap. All right, so let's get started with this. First thing we do is create a new Bruce Banner, which means we're going to call the Bruce Banner constructor. So we're going to go into that class, call the constructor. Constructor takes no parameters, so there's nothing to do here. And then all of the code outside of the methods is executed. While we're constructing the Bruce Banner class, we have a reference in the keyword this, which is a reference to the Bruce Banner object that's being created. So now that, how to run the debugger. I should mention that. I can't say this enough times. I set a breakpoint. I clicked in what we call the gutter over here, and I set a breakpoint. And then instead of running the file, you have the green arrow and then that bug option. I clicked that bug option that looks like this when I run that file instead of the go button. It drops down here. I can't show you the drop downs because it won't show in OBS. But click the debug, and then after you run that file once, then you can click the debug up here. That runs the debugger for you. So we're inside the Bruce Banner object. We have a reference to the Bruce Banner that's being created. You always have a reference to the calling method, or the calling object. The calling object for the constructor's sake is the object that's being created. And this is what's actually going to be returned when the constructor resolves. The constructor is going to return that reference. So we have a reference to the Bruce Banner that's being created, this at 816. We're going to step into the code once, and we get to the first and only line that's part of the initialization code for Bruce Banner. Any code that's outside any of the methods, that will be executed once, and it will be executed when the constructor is called. So the constructor is called, no parameters, execute the code that's outside of this, and for this we're going to create a new Dr. Banner object, and we're going to give its constructor a reference to the Bruce Banner object that's being created. So the Bruce Banner object that's being created, that's going to be the constructor argument to the Dr. Banner class. And when we're creating that Dr. Banner class, this banner of type Bruce Banner is going to be equal to this in this stack frame, which is a Bruce Banner at 816. Whenever you see this at and then a number, you know that that's an object on the heap. So this Bruce Banner class is on the heap at some memory address at 816. We have in that banner variable that same object, a reference to that same object on the heap, that at 816. Now this is a reference to the Dr. Banner class that's being created, which we happen to get at 819. The numbers here don't really have much meaning, but they just show us that this is, they have to be consistent. It shows us where this thing is on the heap. This one's at something that's referred to by 819, by that number. The Dr. Banner class extends the state class, so we have to call the state constructor as well. We're going to just forward that banner object to the state class, and here this is still a reference to that Dr. Banner that's being created. It's still being a reference to the Dr. Banner that's being created. Even though we're in the state class, we have a reference to a Dr. Banner object. We're going to assign banner the reference that was forwarded, this at 816, the Dr. Banner that's currently being constructed, and then we're done in the state class. All it needed was that banner variable in its constructor. We're also done in the Dr. Banner class, and we're done creating this Dr. Banner. So now, in our main stack frame, we just had two stack frames, a stack frame for each constructor call. Those two stack frames returned, and they returned references to the objects that were created. So this new Bruce Banner returned that Bruce Banner at 816, which has a state of Dr. Banner at 819, which has a reference to that Bruce Banner at 816, and we have a little bit of a cyclical composition here. If we want to go through all that, the state Dr. Banner has a reference to the Bruce Banner that it's attached to. That Bruce Banner has a reference to the state that it's currently in. So we have a little bit of cyclical composition there. Maybe you'd want to get rid of that, just the way I have things set up here. So we have this Bruce variable of type Bruce Banner that stores a Bruce Banner object that's on the heap that's at 816, whatever 816 means. We create a new car. We don't really need to think about that too much, but we do get a new car on the heap. It's another object on the heap at 821 we got as our kind of randomish number. And we're going to call our first method, Bruce.useCar. Whenever we have the dot operator, we're taking a reference and following that reference over to the heap and doing something with the object that's referred to by that reference. So this is saying, hey, Bruce, you're a reference. I don't give a damn about references. I give a damn about the object you refer to. So we're going to take this at 816, follow the instructions, like the roadmap of how to navigate the heap and find this Bruce Banner object. We're going to go to the heap, find that object, and then access its state and behavior. In this case, we're going to access the behavior and call its useCar method. So we're going to travel to the heap, following this reference, find that object, and call its useCar method. And whenever we call a method, this, the keyword this, is going to be a reference to the calling object. So what reference, how did we get here? How did we get where we are right now? This is going to tell us that. So inside this method, for this specific method call, this is a reference to that Bruce Banner at 816, the same reference that's in that Bruce object in the main stack frame. So in the main stack frame, Bruce refers to it at 816. In this use car stack frame, this refers to the same object. Some of you pointed out, like, why do you even use this? Like, you could do this same thing. You could delete this dot. That still works based on scoping. Like we talked about with code blocks. I say state. Scala is going to look for a variable named state. It doesn't find it in this stack frame. So it does go out to the next scope, which is the object itself, and it finds a variable named state. So it will find that. I like to use this dot to be absolutely clear, and sometimes I do forget it. But this dot makes it very clear that I'm accessing a state variable. Makes my code more readable. It communicates to other developers that, hey, this is what I'm doing. I'm changing something. I'm accessing the state of this object. On the stack, there will be this. Yeah. So this is on the stack, storing a reference to the object that's being called. So this is a whole stack frame right here. Just ignore all this red text up here. This is other stuff in the repo. Most of this is other stuff in the repo. This is going to go on the stack in that stack frame and contain a reference to the object that called this method. Car, a reference to the input parameter, that's also on the stack. But both of these have references to objects that are on the heap. These are only references to objects on the heap. The objects themselves are not on the stack. But this, which is a reference to the object, that reference itself is on the stack. Yeah, this value reference. Exactly. And I don't think I ever showed that in the slides, so I'd have to be lenient on it for the quiz. That this is on the stack. But yeah, this will be on the stack. The reference to the calling object. All right, so we get that behavior. We didn't get there yet. So this dot state, so follow the reference this to the heap and access its state and behavior. This time we're accessing a state variable named state. That's this Dr. Banner at 819 dot use car. So we're following another reference. We're following it to this variable named state, which stores a reference to this object Dr. Banner at 819. And we're going to access that object. We're going to say, state, I know you're a reference. I don't care about your reference. I care about the object you refer to. So navigate to this object, which is Dr. Banner at 819, and call its use car method on this car. So we're going to follow that reference, find a Dr. Banner object, an object of type Dr. Banner. We're going to call its use car method. This is now a reference to that Dr. Banner at 819. That's how we got here. That's the reference that we followed to get here. And we have a reference to that same car. We're going to call the car method. This is stuff we've already seen. I'm not going to go over conditionals. That stack frame returns. This stack frame returns. And we're back to the main method. A lot of that's review, which is probably pretty needed. The heap is still pretty new to us. But now let's get into a state pattern thing. We're going to call Bruce's make angry. So Bruce.makeAngry. This is now a reference to Bruce Banner at 816. We're going to access that object's state. Same thing we just saw. State is a Dr. Banner, and we're going to call Dr. Banner's make angry method. Okay, now in make angry, this, see, I don't have my this right here. I should have this dot. But that's perfectly valid. It still works, but it's more clear if you have this dot. So this is a reference to that Dr. Banner state, the object of type Dr. Banner. This has an object named Banner, or a state variable named Banner, which we're going to access. So we're going to say this Dr. Banner object go to the heap and access your banner variable and access its state variable. So we go this dot banner, which is that Bruce banner at 816, the object to which this state is attached. Access its state variable, which is Dr. Banner at 819, happens to be this object, a reference to the state that it's currently in, which is this state, equals new the Hulk of banner. So we're going to take this banner, this too. Even in this very example, I missed a couple. This dot banner, we're going to access this banner object, or this banner reference, pass that to a new instance of the Hulk, call its constructor. So we are creating a new the Hulk at 957, so we get a brand new object on the heap. It happened to be at 957, just happens to be wherever it was created. So now, in this context, this is going to be a reference to that Hulk that's being created. Banner is that at 816. We're going to store that in the state variable for this. We're going to put that right there. Call the state constructor, which just forwards that banner, that reference to a Bruce banner. That returns, the Hulk returns, and our new Hulk that we just created is going to be assigned to this.banner.state. This.banner.state is no longer going to be an object of type Dr. Banner. It's going to be an object of type the Hulk. So now, after this make angry call, Bruce .state is now storing a reference to an object of type the Hulk at 957. So we just had a state change because the state variable in the Bruce Banner object has been replaced with a new object of a different type. Instead of having an object of type Dr. Banner, it has an object of type the Hulk. So now, next time we call a method, use car in this case, everything else is the same except that state is an object of type the Hulk. So when we say this.state, this, follow your reference to the heap, access your state variable named state, follow that to the heap, it's going to find an object of type the Hulk, and now useCar is going to be a different method. We're going to get car.smash instead of driving the car normally. So we got different behavior from the same exact method call. We did Bruce.useCar, same exact method call twice, but since Bruce is now in a different state, we're getting a completely different method call. The implementation of the useCar method and the behavior of the Bruce Banner object is completely different because the state has changed, because the type of the state is different. It's a different type of object. They're both of objects of type state because they both extend state, but since they're different objects, different inheritance, different objects, different classes that both inherit state, we get completely different behavior. And of course, no conditionals, except in the car class, which I'm glossing over, which we could get rid of. I should probably just get rid of them. But we get completely different behavior because of the type of that state variable. Learn control. And I'll just breeze through the rest of this because I think I made my point here. Learn control, we're going to have another state transition. We're going to access that Bruce Banner object. We're in the Bruce Banner class right now. So the Bruce Banner object that called this method, .state, go to the heap and access its state variable named state. And replace that, whatever it was storing, replace it with a new Professor Hulk state and give it the Bruce Banner object so it knows the object to which it's attached. Same thing, Constructor just takes that Bruce Banner reference and returns it. And now Bruce's state is Professor Hulk, which happens to be at 959 on the heap. Now when we fight, again, defer to the state variable for the fight behavior. State is now Professor Hulk. So again, we get different behavior based on the type of that state variable. Not based on its value. Its value is just a reference. We don't really care what those references are. It just says, hey, here's where you can find an object on the heap. But once we follow that reference and find that object, based on the type of that object, we're going to get different behavior. Based on type, not based on value. Then we can call make angry and calm down. Nothing happens because we're in the Professor Hulk state, which we can't escape. Calm down. We get Professor Hulk's calm down method. And then everything's destroyed off the stack. Any other questions on this example before we go to the next one? That is a lot, but a lot of it's details that you can do this yourself. You can go through the debugger and slow it way down and go at your own pace. I'm just showing you how the slides apply to code. So then you can play around with coding examples and explore them for yourselves. And what's on the quiz? Everything's on the quiz. You should know everything going into the quiz. The syllabus tells you what's on the quiz also. Think it's finally sinking in? Nice, Technocat. Yeah, exactly. You can do your interview from bed, but you might have to turn on your webcam. If the TA asks you to turn on your webcam, turn on your webcam. So do it from bed, but like put on a shirt. What are the answers to the quiz? Yeah, actually, I can go over the answers to the quiz. Watch these lectures. Actually, I won't ask you about GUI. Watch these lectures. I guarantee every answer to any question on the quiz, you'll be able to know them based on that. I already gave you all the answers. If there are no more questions on this, let's switch over a little bit. Oh, I already have this running. And I want to show you, once I get my stuff up right, this thing. Did I? Ooh, I didn't download the slides yet. Yeah, all the classes extended state except the Bruce Banner class. I didn't download the slides yet. Let me do that. Let me make sure these are updated. Save. Jumper is back. Jumper's a little tough for this lecture. I really like this example. There's so many moving pieces. We really get a lot to talk about. But it's a little tougher because we didn't do the physics engine homework. So this is Jumper. This should be the best way to do it. So this is Jumper. If you know someone in the other section, they're actually doing the physics engine homework. You can ask them how it's going and stuff. But they actually build the physics engine for this to get this to work. I do have to restart this. It'll make more sense. But we're not doing the physics engine assignment this semester, in this section at least. So we miss a little bit of background. You can't actually implement this and get it working. I mean, you can if you don't mind doing an extra homework. But this is a game with a physics engine attached to it, and then for your homework, you would make the physics engine. So this game, I do want to explain what the game is, though, is we have two characters here, and they jump, as Jumper implies. And what I want to focus on is the jumping behavior of these characters. So first, the goal of the game is to climb higher than your friend, faster than your friend, and once your friend hits the bottom of the screen, they lose, and they can't move anymore. The jumping behavior is you hit the jump button and you jump. Fair enough, right? If I'm standing still, this is the maximum height I can jump. If I'm walking and then I jump, I can jump farther, or I can jump higher based on that. I can also jump higher or shorter depending on how long I hold down the button. And I also have a double jump that you should be able to jump one extra time while you're in the air. So we have pretty complex jumping behaviors in this game. And a lot of the behaviors, if you played any platformers before, you would expect a lot of these behaviors. Whenever I play a new platformer, one of the first things I try to do is double jump to see if I have that feature. We also can double jump after walking off a platform here. And if you turn around midair, you actually go slower when you're changing direction. So we have quite a bit of behavior here that we want to implement in this game. So let's implement it. I could have left that open, I guess. So let's implement that. That's what we want to look at today. And the doodle jump is what gave me the idea for that. And while we're talking about this, of course, the goal is to get lecture task 6. Some of you have pointed out lecture task 5, and I did in lecture Friday. Lecture task 5, you don't technically need any state pattern to do that. You can do that with everything being in the same state, because all the buttons have the same behavior no matter what. Nothing changes. Lecture task 6 is specifically designed to make you have quite a few, a decent number of states here. So first, our goal is to implement the rest of the checkout machine to get the functionality that we would expect for a customer to be able to check out all their items and pay for them. Some things are just simulated, of course, but we're not actually transferring funds. We're not accessing banks, but we're getting that functionality. So first, when the checkout machine is first created, you should display some welcome message to your customer saying, "Welcome to my store," or whatever. Any message, any string that contains the word welcome is going to be valid. So, for example, if your welcome string is "hello and welcome to my store," that contains the word welcome, so it's valid. Don't do equal welcome. Do contains welcome. Pretty easy to mess up, but make sure you don't miss that containing. That's why we have this example and everything. Yeah. If a customer enters an empty barcode and they've just scanned an item, and with these, by the way, there's always more detail in the official document. I cut these down to fit them on the slide more better. So there are edge cases and things that I talk about in the doc. But if the customer hits the enter button right after scanning an item, it should scan that item again. And then once they hit clear or any numbers, that feature is turned off and they can no longer rescan that item by hitting enter. So that, of course, you should be thinking, well, that's a new state. Am I in the state where the enter button will rescan the previous item? Or have I moved away from that state and I'm in the regular entering numbers to scan items state? You should be thinking state there, of course. The checkout button is going to allow the customer to say, "I'm done scanning things. I'm ready to start paying." When the checkout button is pressed, no more items can be scanned. So if they hit checkout 1, 2, 3, enter, that shouldn't put error on the screen. That shouldn't put an item on the screen. That shouldn't do anything. Those buttons should effectively be disabled. So no more items can be scanned. We're going to display the string cash or credit, the exact string this time, not a string containing cash or credit. And add the following lines to the receipt line. So receipt lines should not only return all of the items that have been scanned with their prices, but also the subtotal, tax, and total of the purchases. The subtotal is the sum of all the prices of the item, i.e. calling the price method. So everything that's displayed on the receipt, add all that up. The tax should be the sum of all taxes on all items. So go through all of the items that have been scanned, call their tax method, and sum up all of that tax. And then a total method, which is subtotal plus tax. When the customer hits either cash or credit, and cash or credit have identical functionality here, once they hit cash or credit, display a string containing the string thank you. Like thank you, come again is what I did in my solutions. A string containing thank you. Clear the entire receipt and start getting ready and get ready for the next customer. So then the next customer should be able to scan items again. You should be in some sort of initial state where the user can start scanning, entering barcodes, etc., and start getting that done. And then add your test suite LT6. LT6 is going to mess with my LT5 code. Yeah, so the whole point of LT5 was to set up the foundation for LT6. So you weren't forced to use the state pattern in LT5. Maybe I should have added like the welcome message and got something in there. But your LT5 code is the foundation for your LT6. And LT6 is where the action's happening. This is where we're really building the self-checkout machine and building the functionality that your customers will expect. So you already know how to do that. We already talked about the state pattern. I want to give one more example and a more complex example that's going to reinforce how to get that functionality in LT6, that functionality LT6 asks for. So this is Jumper that we just saw the demo of. This is a vertical 2D vertical scrolling platformer where you got to climb faster than your friend. What we want to talk about is how we actually move in this game. We're going to ignore the physics. I cut out some slides about physics if you looked at the slides earlier, because we didn't talk about physics at all this semester. And I want to focus on the button presses that a user can hit. So to move, we're going to take these user inputs and convert them into all of that behavior that we saw in the demo. And of course, we're going to use states. That's what we really want to talk about. So there's only 3 buttons for each player, left, right, and jump. For player 1, it's ADW. For player 2, it's the arrows. So when I was controlling both players, I just got one hand on WASD, one hand on the arrow keys, and I'm moving both players. So how do we convert those inputs into actual movement in an actual game that you can navigate and have pretty complex jump behavior? How do we do that? That's what we want to ask. First, we're going to define what that jump behavior actually is. So let's go through these. I went through most of them in the demo, but just in case I missed one, we can left to right is going to walk left to right. Jump is going to jump. Easy enough so far, at least. If we left it at that, this would be pretty easy. We can jump higher while walking than we do if we're standing still. We're going to jump different heights based on how long we hold the jump button for. We're going to move left or right slower in midair if we change direction during our jump. We can jump up through platforms, but when falling down, we should land on platforms. If we walk off the edge, we should fall. And block all inputs if the player reached the bottom of the screen. This is all of the functionality that we want in our Jumper game. This is what we want players to be able to do. This is what the user should experience, is all of these features. And by the way, any platformer any decent platformer, I should say, has pretty complex movement behavior. Like, this is a pretty short list, but you would expect these kinds of behaviors depending on the game you're playing. There's actually really complex mechanics to a platformer. It might seem simple. Yeah, you just move left or right and jump. But there's actually quite a bit going on. To get a game like Mario to feel good, there's a lot going on. Yeah, exactly, feelish. To get a game like Mario feeling good, to have it feel good to control Mario, that doesn't just happen. The developers have to do a lot of coding and a lot of playtesting too to get that behavior. This gets us pretty good feeling controls in this game. I don't know, I like it. I like the way this game controls. But I'm biased, so it doesn't mean anything for me to say that. So we could do this all without the state pattern. Yeah, in Super Meat Boy, that game controls awesome. That doesn't just happen. And that is what that game is just being able to control Super Meat Boy. It just feels good. The controls are responsive. Everything's just it's very tight controls, as they say. You don't just get that by slapping together a few lines of code. That's very complex movement behavior for that game. And any platformer lives and dies by how it feels to control that player. It takes a lot to code that. So we could do this without the state pattern. It'd be tough, but we could do it. And this is one case where we're going to start seeing the benefits of the state pattern. This would be a complete mess, in my opinion, without the state pattern. Granted, if you have some other way of organizing your code, you can do it in a great way without the state pattern. but the state pattern is going to make it pretty clear how to make this cleaner with our code. And it would be very difficult to add new features. So just a foreshadow, a little bit of spoilers for the lecture, is we're going to explain all the behavior that we saw on this slide. But one feature that I showed off in the GUI that I didn't mention here is the double jump. So if we build all this, if you were to build all this and I said you can use conditionals, you can use whatever you want, just go ahead. You submit that and you're like, Autolab's satisfied, I got all the features Jesse asked for and everything. And then after the deadline, I say, okay, you have a couple more days, add double jump to your game. How hard is that going to be based on your design? We're going to see with the state pattern that it's going to be no problem at all. It's going to be super easy to add new features. Just like doing the application objectives. The application objectives are tough on their own right, but it's not going to be hard to add those to your existing functionality without breaking the existing functionality, assuming that you have a well-designed state pattern. So let's break this down and talk about how to approach a problem. As of course, this is what you have to do in LT6. How do you approach a problem and apply and design the state pattern for it? And this is where we're shifting to at this part of your careers, is it's more design. How do I approach a problem and design my software and build the architecture for my software to solve this problem and implement these features, and less so about, okay, how do I actually code this up? By now, you should all be pretty damn great at coding. If I give you, write a method that takes these inputs and outputs this, you should all be pretty damn good at that at this point. If you're not, you got some practice to do. You'll get better. But at this point, you should be starting to think about how to design software. How do I back up a step, go to a whiteboard and plan out what I'm going to do, and then go to the code and implement it? Ideally, plan it out on a whiteboard, write up your unit tests for it, and then implement the code. Should be a really solid process for you by this point. So let's go through these steps. These are my kind of recommended steps to approaching a state pattern question. First, write your API. What methods can be called? What methods does my code have to react to? For your homework, this is easy. It's the methods that I provided in the self-checkout class. All those stubbed out methods just say to do. That's your API, and they all correlate to the buttons on the GUI. So the API are all the GUI buttons that the user can press, and that's the only thing your software can interact with. And then outputs, you have the two output displays. That's the only way a user interacts with your software. So that's the API. That's the top level API. That's how the user interacts with your software. So those are the methods that you have to implement. You can write many more methods on top of that. That's fine. But those are the methods that define your API, how the user will interact with your software. One method for each button. Well, I guess not the number button. The number button contains 10 buttons, the number method. Then decide what states should exist. What different states can my software be in? And specifically, this is anything that the user does where any API method should have different behavior. That's going to be a new state. So if there's ever a button that a user presses that changes the expected behavior of any of the other buttons on your GUI, that's going to be a state transition. You're going to change states. So how do these states transition between each other too? For this case, when does a user hit a button that changes the behavior of the player? That's going to be a different state, and you're going to need a state transition between them. API is Application Programming Interface. It's a pretty general term we use a lot in computer science and programming. It's a way that other users are going to interact with your code, or other programmers, the methods that they're going to call on your code. It's the way people from the outside of your code interact with your code. So let's break these down one at a time. We'll write our API, we'll decide what states exist, and then determine the state transitions. So the API, we're going to scan through the specs and figure out which parts of this spec are inputs that are being called from outside of my code. For this one, it's fairly straightforward. It's the buttons that the user can press. They can press the left key, the right key, the jump key, and they can also release those keys. For example, they should jump differently based on how long the jump button has been held. Well, we're going to need to know when the jump button was pressed and then when it was released to figure out how long it has been held down. And that's going to get us that feature. But we do need when they're pressed, or when they're, when they're pressed, it's fine. When they're pressed and when they're released. So 6, we got 2 pressed and released for each left, right, and jump. So we have 6 methods there. Left pressed, left released, right pressed, right released, jump pressed, jump released. I also have another method. I added it here just in case you're going through the code and looking, is the land on platform method, which determines the behavior, what happens when a player collides with a platform and lands on it. We do need a state transition there, so we do need to know, the game has to tell us when we've landed on a platform, so we can know that we're no longer in the in-air states. Speaking of states, decide which state should exist. We're going to look through this and look for the kind of action words, those verbs. What can we be doing that's going to be different states? If we pause through this code, this spec, we're going to see standing still. We need different behavior when we're either walking or standing still. That better be 2 different states, because our API methods, our jump button specifically in this case, is going to have different behavior whether we're walking or standing still. We can jump, so we have to have some in the air states. What I'm doing in the air. Platforms, we have to have different behavior whether we're jumping up through a platform or falling down through a platform. I like to do this by having 2 different states for either jumping up into the air and rising, or am I in the air and falling. 2 different states for that, and then when I collide with a platform, I can say, well, if I'm rising in this state, I'm going to implement different behavior. If I'm falling, I'm going to implement different behavior. If I'm falling, I'm going to land on that platform. If I'm rising, I'm going right through that platform. And then blank all behavior out if we reach the bottom of the screen. So we need one more state for player lost the game. Then state transitions. Again, we pause through this code. If we press the left or right buttons while standing still, so our initial state will be standing still. If we press left or right, we'll enter the walking state. If we're walking and we release the left or right button, we're going to go back to the standing state. And we don't have momentum in this game, so we're going to immediately stop. If we're walking or standing and we hit the jump button, we're going to transition to the jumping state. If we walk off a ledge, we're going to enter the falling state from the walking state. When we land on a platform, we're going to go transition back to the standing state. And in my code, I have something to know if left or right is being held down. We're actually going to transition to standing, and then on the next frame, we'll transition back to the walking state. So I have 2 state transitions in back-to-back frames, if you're wondering how that works. And then if we're... the one case, the reason why this can't be a homework, why it has to be a lecture example, is in the jumping state. If we're jumping up to transition to the falling state, we do that when the apex of a jump is reached, which I tried and tried. I don't think there's a way to do this without a conditional. So this pretty much quarantines. That's probably a bad word for this context. But we're going to confine this jumper game, this state pattern, to lecture slides and lecture examples. Can't really be a homework because I can't get around this one. I need an if there. Too soon. We're still living it. That's why that word came to mind, of course. But and then no matter what state we're in, if we reach the bottom of the screen, we're going to game over. So I like to visualize this as a state pattern or a state diagram. So when we draw the state diagram for this, we're going to create a class for each one of our states. We're going to create an abstract class that each of these states inherits, which defines the API. The abstract class defines the API. It's going to have left pressed, left released, etc. methods. The player object itself is going to defer to the states for their behavior. And And the state diagram tells us how these states are going to transition between each other. So our approach here is to implement the API for each state. If I'm falling and left is pressed, if I'm falling and right is pressed, if I'm falling and jump is pressed, what do each of these buttons do in this state? What do each of these buttons do in this state? What do each of these buttons do in this state, etc.? And implement each one of those classes. While we're implementing them, some API methods are going to create state transitions, and we're going to create those transitions to change the state. If we're in the standing state and somebody hits jump, we're going to transition to the rising state and get all the rising behavior. We hit the apex of our jump, we're going to transition to the falling state. If we land on a platform, we're going to transition into the standing state. If we press left or right, we're going to transition to the walking state, etc., etc. This is how we're going to move around our code. And each time we change states, the entire behavior of the player changes. So in the standing state, the jump button jumps. In the rising state, the jump button doesn't do anything. So we implement each method from the state class differently depending on the specific state we're implementing at that time. By the way, I won't have time to go in the code, but the code is in the repo. I added a big example. Pull the repo and you can see all of this, all the code for this. I can go over some of it after lecture, but I won't have time during lecture to go over it. So we have the state abstract class, which is going to define the API that we can call. All the methods for which the attached object, the player in this case, is going to defer behavior to the state. All of those methods are going to be in the abstract state class, and that's going to be implemented or extended or inherited by all of the concrete states. So our game over, falling, rising, walking, standing. Now when you get to this point, and for your homework, especially when you get to the application objectives, it's very helpful to have additional abstract classes. So here I noticed that rising and falling have a lot of shared behavior, and walking and standing have a lot of shared behavior, a lot of the same behavior. So I can do what we initially did with the dodgeball and health potion classes, where we abstracted out the common behavior. And I'm going to do that here. I take standing and walking, and all of the common behavior, I'm going to factor it out and put it in this on-ground class. This is an abstract class. It extends state, so it has an obligation to implement all these methods, but it's not going to implement all of them. But it will implement any method that is the same whether you're standing or walking. So like hitting the jump button is going to do the same thing whether you're walking or standing. Oh, that's a bad example because walking jumps higher. Hitting the left or right buttons is going to do the same thing whether you're standing or walking. And then anything that's different between the two, those methods are implemented in the standing and walking classes. Same thing with rising and falling. You're in the air for both, so they're going to have a lot of the same functionality. Factor it out, put it in a separate abstract class, implement some of the API methods, and then any rising or falling specific behavior implement in those classes themselves. But wait, how do we add more features? We want to add double jump to this. Well, it's no big deal. We just add some more states, add the state transitions, and we're done. With poor design, this could be very difficult. With our jumper, with our state patterns, we're going to add, I'm going to skip through some of this. We're going to add a couple more states and say if you're rising and jump is pressed, you're going to enter a rising after double jump state, and hit the apex, you're going to enter a falling after double jump state, which these states are going to be identical to rising and falling, except we're going to update rising and falling so the jump button jumps a second time, and then the rising after double jump and falling after double jump will extend rising and falling respectively, except they will disable the jump button. This map is scary. This one does get a little cluttered. Once we add too many states, things get a little wild with the state pattern. And we can do that by extending falling and rising, and then just overriding the jump button pressed to do nothing. And then we can just effectively disable the jump button after you jump once. And now we have a double jump. And very quickly, I'll go through this real quick. We're closing up the state pattern. I want to go quick recap over the pros and cons. The pros of the state pattern, it helps you organize your code, especially if you have a single class with very different with very different behavior depending on its state. And it's very easy to implement this. Each state, you're concerned with one thing. For this method, when the object is in this state and this thing happens, this API method is called, what should the behavior be? Methods are much easier to write, and it's easy to add or change or modify or expand or add features to your software using the state pattern. It's very easy to add things without changing your existing functionality, which is a very nice thing to have. You know, to constantly be worried about breaking things when you're adding new features. The cons, there are a bit of cons, I don't talk about them too much until now, is if you only have a few states or behavior that's not too complex, like the car class in the Hulk example, it can be just a little bit too much overhead to add the state pattern to a simple class. So it can be overkill if you're just using the state pattern everywhere. It can get a little out of hand. And it can change the appearance of complexity in your code. You'll be adding a lot more classes, so it might take a lot of clicking around through your code to tell all the behavior. This is why I like the state diagrams. You look at the state diagram, it's a lot easier to see the behavior of the class. If you're just looking at the code, it can be pretty difficult to read the code for the state pattern. You can read the individual ones, and if you know the state pattern and what you're looking at, it can be easier, but it can be a little tough to follow all the state transitions and how that object is going to behave in a particular program. That's where debuggers come in, that's where state patterns come in and help us with that. So don't use the state pattern everywhere. I'm forcing you to use it now. This is not a realistic constraint. This is just to force you to use inheritance and polymorphism. Out there in the world and after LO2, it's up to you to decide when you want to use this pattern, if you want to use it at all. So when we move into LO3, LO4, when does the state pattern apply? When do you want to use inheritance and polymorphism? When do you want to use those things? So hopefully you'll see by the end of LO2, by the end of the homework, what are the advantages, what are the disadvantages, and you can make informed decisions on when to use this in your life beyond this class.